I'm going to talk about Lewis structures for organic compounds. Organic chemistry deals with primarily carbon and hydrogen containing compounds. Now there's a huge variety of carbon and hydrogen containing compounds, so they had to separate that part of the periodic table from the rest. And so organic chemistry is a study, research, and application of carbon compounds, but not all carbon compounds are considered organic. For example, carbonates, cyanides, carbon monoxide, carbon dioxide, and a few other carbon-containing compounds are called inorganic, not organic. But pretty much inorganic chemistry deals with the entire periodic table. Organic chemistry just focuses on carbon, and it's just because of the rich variety of carbon compounds that are found. It's got a rich variety because carbon doesn't mind bonding to itself. I mean, carbon has no problem forming chains. So what we'll see is that carbon likes to form 4 bonds. Those 4 valence electrons. And so it could form 4 single bonds, form 2 double bonds, or double and 2 singles, or triple and a single. And so there's a lot of bonding variety in carbon. Hydrogen only forms a single bond here. If we look at nitrogen, nitrogen likes to form 3 single bonds, or maybe a double and a single. It's capable of forming 3 bonds. Oxygen is capable of forming 2 bonds. Fluorine's capable of forming 1 bond. And the bonding arrangement changes depending on the formal charge. So for example, sometimes oxygen forms 3 bonds. In that case, it's going to have a positive formal charge. So if the charges are non-zero, then we can change the bonding environment. You know, carbon likes to form 4 bonds, but sometimes it'll form 3 bonds and have a lone pair, which the formal charge would be negative. But when we do Lewis structures for organic, we don't normally total up the electrons. So let's look at some examples of what we do for organics. Now, organics are classified depending on the structures and the composition. So one composition is called the hydrocarbons. Hydrocarbons just consist of hydrogen and carbon. And the structure we can have are alkanes, alkenes, and alkynes. Alkanes, everything's single bonded. Alkenes will have a double bond. Alkynes will have a triple bond. So that's the difference. And so let's look at some simple alkanes. These are some simple alkanes. All these are hydrocarbons because they all consist of carbon and hydrogen. Just carbon and hydrogen. Carbon and hydrogen. One thing that these all share in common is the carbon-hydrogen bond is nonpolar. And so all of these molecules are nonpolar molecules. That has an impact on what it dissolves in. And so here we have butane. Butane is a 4-carbon chain like this. And the rest are hydrogens. So we fill each carbon with 4 bonds, basically. It's butane. This is isobutane, a different arrangement of 4 carbons. In isobutane, there's this little tail here. This is like a fish tail. This fish tail part is the iso. So if we see a structure like that, it's iso. It has these 2 CH3s attached there. So isobutane. Isobutane can also be called 2, or not, we don't even need the number. It could also be called methyl, because these CH3 groups are called methyl. Propane. Prop means 3 carbons, so this could be methylpropane or isobutane. Up here, pentane has 5 carbons, so this is the structure here. This would be isopentane. This would be neopentane. The interesting thing is all 3 of these structures have the exact same formula. They all have 5 carbons, and they have 12 hydrogens. So all of them, but their structure is different. And so when we have the same formula but different structures, we call those isomers. So these are 3 isomers of this particular formula, C5H12. Now, what do we do when we're drawing Lewis structures? When we're drawing Lewis structures, I don't normally total it up. And so let's draw the Lewis structure of this. going to draw the Lewis structure for C2H60. C2H60. Now, normally we figure out the total number of valence electrons and go from there. But another way of doing this is just by looking at the little structural units that we can have. For example, if we have two carbons, we'll link them together. Carbon doesn't mind being linked together. Unlike oxygen, oxygen doesn't like to be linked together. And then we can throw on the hydrogen, maybe. You know, carbon likes to form 4 bonds, so 4 single bonds like this take care of 3 of the hydrogens. And then we'll throw the oxygen over here into this carbon. So maybe we'll end up with a structure like this. Okay, and then oxygen likes to form 2 bonds with 2 lone pairs. So there we have it. Now, how do I know? Well, we know that, you know, carbon's going to contribute 4, hydrogen's going to contribute 1, oxygen's going to contribute 6. If they contribute these and they end up with that, then all the formal charges are 0. And so the alternate way of looking at this is if all the formal charges are 0, then all the valence electrons are accounted for. And so when we look at it, what are the formal charges? The hydrogens are 0. This carbon is 0, 0, 0, 0. So this is a good structure here. This is called ethanol. Yeah, ethanol is an alcohol. It's an alcohol because it has the COH group. Alcohols are, they're going to have this, it looks like a hydroxide ion, the OH, but it's not. It's not a hydroxide because hydroxide would be OH minus and it would be ionically bonded, but this OH is covalently bonded with carbon, so it's the COH group. The OH is part of this is called hydroxyl, not hydroxide. Hydroxide would have another lone pair here instead of a bonding pair. And so this is what distinguishes this as an alcohol. You know, this type of structure has certain properties that are characteristic of alcohols. This is 2 carbons. When we have 2 carbons, it's F. It's ethane. Ane is all single bonds, so it's like an alkane. It's all because it's an alcohol. So this is ethanol. Ethanol is called grain alcohol or sugar alcohol. Did I talk about wood alcohol?
Yes.
Methanol? Well, this is one structure, and normally we put the least electronegative element in the center, but oxygen doesn't mind being in the center too, because oxygen likes to form this kind of this single bond link. And so another structure we could draw for this particular molecule is like this. Well, we'll throw the oxygen right in the center and then have these 2 CH3s attached to it. CH3 itself is called methyl. You know. So this is a methyl, this is a methyl. This COC link is what we call an ether. And the name for this is dimethyl ether. Dimethyl ether. The interesting thing is both of these have the exact same formula, but they have different structures. So they have different structures, they're going to have different properties. And we call these, what do we call things that have the same formula but different structures? Isomers. So these are 2 isomers for this. And so if we have C2H60, I don't know. Are we talking about ethanol or are we talking about dimethyl ether? I don't know.
So that was same formula, different structure?
Yeah, same formula, different structure. And so these would be 2 isomers of this formula, C2H60. Yeah, the properties are going to be quite a bit different, whether we have a COH link or a COC link. Here, this one, do you know what this one's called? Well, this one has a COH link, which would be what type of group? Yeah, a hydroxyl group. This would be an alcohol. Alcohols are the COH link. And alcohols alcohols are going to have certain properties. This is a one carbon alcohol. One carbon is called meth, and so this would be methanol. Methanol, this one can cause like permanent blindness, death. Every year, a large number of people die of methanol consumption. They call methanol wood alcohol. You know what wood is made of? Cellulose. Do you know what wood is made up of? Wood, cellulose, is made up of glucose. You know, glucose is a sugar. So wood is made out of sugar. Does wood taste very sweet? No, it doesn't. It doesn't taste very sweet to us, but maybe to termites it's extremely sweet. But anyway, people who try to ferment wood will end up with methanol. You shouldn't ferment wood, you should ferment sugar, and then you'll end up with ethanol. Methanol's pretty deadly stuff. Just one carbon difference. You know what this is? This is 4 carbon in this chain with the alcohol. This is called butanol here. Methanol, 1 carbon, butanol, 4 carbon alcohol. You know pentanol? How many carbons pentanol would have? 5. Okay. These are ethers here. CH3 is what we call methyl, but if we have a CH3CH2, CH3CH2 chain like this we call ethyl because it's 2 carbons. So this is an ethyl group and this is an ethyl. And so the name for this would be diethyl ether. Diethyl, because we have 2 ethyls and we have the COC link. The COC link is the ether link in organic chemistry. Diethyl ether. Diethyl ether is the most common ether. A lot of people just call it ether, you know, but there are a lot of different ethers out there. For example, dimethyl ether, that's diethyl ether. Ether fires are very dangerous. This diethyl ether is normally a liquid, and it's very volatile, which means it vaporizes quite easily. But normally when the vapors, like for example methanol, when it vaporizes, it's pretty volatile. The vapors rise up the ceiling. But when ether volatilizes, you know, ether evaporates pretty easily. When it evaporates, it doesn't rise up. You know, ether falls down to the floor and then starts filling the floor with ether vapor. And so if there's an ether fire, it burns, you know, from the bottom up rather from the top down. So that makes ether fires particularly hazardous. This is also an ether over here. It has the COC link. The COC link, except on the left side we have a methyl, which is the CH3. On the right side we have this ring. This ring, which is this flat ring, is called a phenyl. So this is methylphenyl ether. Methylphenyl ether. So on the left is, or it doesn't matter what side. Methylphenyl ether, we just name them alphabetically. M before P. These are carboxylic acids here. Normally the formulas are written to give you some structural clues to what it is. So for example, if I were looking at acetic acid formula is normally written like this, CH3COOH. This almost looks like a peroxide link, but it isn't. It can't be a peroxide link. And so when we do this, you know, carbon likes to form 4 bonds, this, because of this carbon. This carbon's going to have a double, and then it's going to have a single, this, and then to the H here. Now, if I try to make that peroxide link, peroxides are very unstable, so we try to avoid making those. Acetic acid's not so so unstable. So if I made a peroxide link like this, there's no way to complete the octets with the number of electrons that we have. And so here we'd have to do an electron count because, you know, the carbon likes to form enough bonds to do it. So maybe we'd have lone pairs here. But, you know, the formal charge is going to tell us if it came out ahead or came out behind in electrons because each carbon donates 4, oxygen 6, hydrogen's 1. So if we look at these hydrogens are 0 formal charge, this carbon's 0 formal charge. But when I get to this carbon, what's the formal charge here?
-2.
This is -2. And this oxygen? Actually, the formal charge of this oxygen turns out to be 0. And this one? 0. Basically everything else is 0. And so if I have a -2 charge and no +2 charge, then this whole thing is -2, so it's not going to work. So what I must have 2 extra electrons. So let's get rid of 2 extra electrons. Okay, now what is the formal charge? 0. The formal charge is 0, but do I have an octet there? No, I don't have an octet. And so I need to make an octet. I can make an octet by taking a lone pair off here and go double bond here. But if I do that, then what are the formal charges here?
-1.
Minus on the carbon and plus on the oxygen. See that? And so I end up with this structure. Now I got an octet, but I got this formal charge. Whereas if I drew this structure, are there any formal charges here? There are no formal charges. So this structure would be better than that structure in terms of Lewis. And so if we get this, we get a very strange structure. So this would be the correct structure. And so the 2 oxygens are not bonded to one another. The 2 oxygens are bonded to the carbon, so it goes COOH. This is the way we read it. CH3, COOH. That would be the structural formula. All carboxylic acids will have the COOH group. So for example, if we look at formic acid, it has a COOH. Formic acid is the simplest, one carbon, also called methanoic acid. One carbon, so this goes hydrogen here, HCOOH. Acetic acid would be ethanoic acid with 2 carbons, or acetic acid, CH3, COOH, CH3, COOH. And then this would be propanoic acid with 3 carbons. So this would be CH3, CH2, COOH. Would be it. And so for organic, we do the Lewis structures typically a little different. You know, we think in terms of putting these units together to form an adequate structure. So that's it at the end. Now what I'm going to do is I'm going to go back. We're going to talk about the shapes. The shapes. Shapes of these things are really important. You know, what is wood made of? Wood is made up of glucose molecules. These glucose molecules are linked together in a long chain like this called cellulose. And so cellulose is made up of glucose, 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 linked together. But we eat sugar, don't we? We don't eat cellulose. You know, the type of sugar we consume is, well, sugar, but the sugar is stored in our body as, not cellulose, but it's stored in our body as glycogen. And so glycogen is the type of sugar that we metabolize, you know, when we need it. And so the glycogen here, what is glycogen made up of? Do you know what glycogen is made up of? It's made up of glucose, glucose, glucose. When you look at it, you look at wood and you look at glycogen, they look the same, don't they? In fact, they are. They have the exact same formula. They have the exact same formula. Do you know what's different? The structure, the three-dimensional structure. But when you look at the structure, it looks the same. Structurally, they look the same. The only difference is a very subtle difference. It's the way the bonds are positioned in 3D space, because all the bonds are the same. You know, that's different than looking at ether. Ether has a distinct COC link versus the alcohol COH link. That's a structural difference. Here, we have all the same bonds. All, you know, COC, COH, CC, CH, all the bonds are the same. It's just their orientation in three-dimensional space is different. Well, that orientation in three-dimensional space is critical because the way we metabolize glycogen is we have enzymes, and those enzymes will break apart the links, freeing up the glucose. Our enzymes are oriented such that glycogen's not a problem, but cellulose is a problem because our enzymes don't recognize cellulose because things are out of place. You know, what's supposed to be here isn't. And so, just because of the way the links are, take a look at the COC link here, this kind of ether type link here, is different than in glycogen. And therefore, cellulose we can't metabolize, whereas glycogen we can. This turns out to be an important issue in biology. So, for example, if you have like ibuprofen, you know, when you buy ibuprofen, you know, they can't control. When they manufacture it, half of them come out like this, half of them come out like that. And your body can only recognize one form of the ibuprofen, not both. And so it turns out like half the ibuprofen in your tablet's wasted because your body doesn't recognize it. And so that means that there's tremendous waste. If you make a ton of ibuprofen, then only half a ton is used. The other half is completely wasted. And so this is an important topic in chemistry. In chemistry, people are trying to do this. Let's say this is randomly made. You know, sometimes it links like this, sometimes it links like that. Let's say 50% of the time it links like this, 50% of the time it links like that. So if you were to buy sugar, you know, half the sugar is wood, the other half is sugar, right? And so you eat it, the wood doesn't do, well, wood's fiber, so it'll help you cleanse. But other than that, it's not really good. And it's not the soluble fiber type. Anyway, well, so it's this kind of situation. But trees only make one form. They aren't going to make glycogen. And our bodies only make glycogen. It doesn't make cellulose. And so biological systems are already doing this, but chemical systems, it's when you react these things. Well, anyway, let's talk about structure. And we can get an idea about the structure of these things, three-dimensional structure, by using VSEPR. VSEPR stands for valence shell electron pair repulsion theory. VSEPR is based on this quantum mechanics of light. And anyway, versus the full version of quantum mechanics, which we've only looked for. But valence shell electron pair. Well, electron pair is used loosely. So we're going to start off with electron pair geometry. Pair shouldn't be here. When we think about a pair, we think about two. But this pair means just a group of electrons. So electron pair, don't take it so literally. A pair is just a group of electrons. So let's take a look at what that means here in the next slide. If we look at these, you know, these are single bonds here. Now, single bonds are a pair of electrons, so this works. This works out nicely. But it doesn't have to be two single bonds like this. For example, we could have two double bonds, one double bond here, one double bond here, or a triple bond and a single bond. If we have two groups of electrons, then the two groups of electrons repel each other. Therefore, they want to be as far apart as possible. And to put two groups as far apart as possible, we'll have to maintain a 180-degree angle between them. That's with two groups. If we have three groups of electrons, we want to orient them as far apart as possible, and they would adopt this orientation where they're 120 degrees each other, maximum distance. Okay, so as far as electron pair geometry goes, this we call a linear EPG. A linear EPG, meaning a linear electron pair geometry. This one's called a trigonal planar EPG. So it forms a planar triangle. This one over here is with 4 groups. If we stick a 4th group here, it's going to push these 3 down. So put a 4th group there, push these 3 down. And when we look at this geometry, this is called a tetrahedral type geometry. Tetrahedral geometry like this has angles of 109.5 in 3D space. It's going to maximize the distance. In fact, all the angles here are 109.5. No matter which of these 2 you pick, it'll be at a 109.5 angle. So we pick these 2. And we look at the shortest angle here would be 109.5 back.
What was the word called again?
Trigonal planar, P-L-A-N-A-R, trigonal planar. You'll see that again here. So one way to visualize these groups of electrons is are like balloons. These balloons want as much space as possible. So when we look at this on here, this is a linear EPG. We have 2 groups. Now the balloons aren't always the same size. You have single bonds, and double bond, double bond, double bond, single bond, triple bond, single bond. So the balloons don't have to be the same. But regardless, if we have 2 balloons, they're going to be at 180 degrees apart from each other. 3 balloons, what do we call this? We call this trigonal planar. Here, this one. They're going to be at 120 degrees. Now, if we put the 4th balloon, it will come up here and then push these 3 down. So that's called tetrahedral. And the angle's 109.5, or a lot of people just say 109. It's simple. It's 109.5 to 4 sig figs. To 5 sig figs is like 109.4, 7 or 48. Or if we do it to 3 sig figs, it's just round to 109. So we could do it 3 sig figs and 109. We don't have to be so precise with these. This is it. Those are the EPGs. Now it gets a little bit tricky because we have an EPG. The EPG is called the electron pair geometry, and it's just the geometry based on the number of groups. We have another geometry. You see that? What's this geometry called? Yeah, molecular geometry. Now, what's the difference between a molecular geometry and an electron pair geometry? Well, the electron pair geometry looks at all the groups around the atom. But a molecular geometry only looks at the atoms around the central atom here, called B. And so that gives us different possibilities. So for example, if we have 2 groups, it's linear. If we have 3 groups, it's trigonal planar. So this is trigonal planar, that's trigonal planar. If we have 4 groups, it's tetrahedral. Tetrahedral, tetrahedral. And so what's the difference between these 2 trigonal planars? Nothing. They're both trigonal planar EPGs. They both have a 120 degree angle. But it depends on how many bonded atoms I have. If you look at this one, I have 3 bonded atoms here. And 3 bonded atoms, so this will be like BF3. It's going to give us a trigonal planar molecular geometry. Whereas this one is trigonal planar, because I have a double bond, a single bond, and a lone pair, so I have 3 groups around it. But when we just look at the bonded atoms, it doesn't look trigonal planar, it looks what we call bent or angular. Bent is a little shorter, so we'll call it bent. And the angle here is 120. The lone pair is not shown here. There's a lone pair here that's pushing these 2 in. If I look at this one has 4. Now with 4 groups, it's going to be tetrahedral EPG, but we have 3 possible MGs for this, molecular geometries. One is we have 4 bonded atoms like this, and so we get a tetrahedral EPG and tetrahedral MG. The other is if we have 3 bonded atoms. If we have 3 bonded atoms, we're going to have a tetrahedral EPG. However, the MG is not going to be tetrahedral. There's a lone pair here that's not shown. And this shape is called trigonal pyramidal. So it looks like this. This would be a trigonal pyramidal. And then here, this is tetrahedral here, but with only 2 bonded atoms and 2 lone pairs. This comes out bent or angular, so this is what it looks like here. This is water. We don't see the lone pairs here. We just see the bent or angular. 9.5. So, normally when we draw Lewis structures, we don't care about the angles. When I draw a Lewis structure, I'm not really paying attention to the angles. So for BF3, I can just do this. It's perfectly fine. Do that. But, that's a Lewis structure. Now, if I want to draw like a more 3-dimensionally accurate drawing of this, this is more accurate 3-dimensional drawing. We're going to call like a wedge and dash diagram. Then I'd pay attention to the angles. Here, I'll try to do that. And so, can you try to draw 3-dimensionally more accurate? If you look at the Lewis structure here, I look at the Lewis structure. Let's look at this one here, which is methane. If I look at the methane molecule here in the Lewis structure, what does it look like the angle here is? The angle here looks to be 90 degrees, but is that accurate?
No.
No. Same thing here. If I look at water, looks like the angle is 180 or 90. Actually, it's neither one of those. And so can you draw, why don't you try drawing these as 3-dimensional as possible? Why don't you draw those, and let me just